Hello, and thank you for joining my presentation. I am Moritz, and I'm a PhD student at the University of Strathclyde. My presentation is titled The Effect of Leading-Edge Tubercles on Wake Flow Dynamics of a Marine Rudder, and my co-authors for this work were Dr. H.L. Shee and Callum Stark. To begin with, what actually are leading-edge tubercles? Tubercles are passive flow control devices that are inspired by the distinctive bumps that can be seen in humpback whale flippers. These whales have a great agility unique to their large body size, and this agility has been attributed to the tubercles. Researchers have shown that the tubercles apply to hydrofoils, prolong flow attachment, increase post-stall lift, and give a much smoother stall performance. All these characteristics are desirable for marine rudders too. But how do the tubercles achieve this? The free stream flow is diverted into the troughs between adjacent tubercles, and pairs of streamwise counter-rotating vortices form behind each tubercle. These vortices exchange momentum within the flow and energize the boundary layer. They also compartmentalize the flow in a similar way to wing fences, which minimizes span-wise flow components and limits flow separation rapidly spreading out. These effects have been shown by several researchers already, so for this work I set out to analyze the effect the streamwise counter-rotating vortex pairs have on the wake behind the marine rudder. There are a number of wake effects that can be reduced by the tubercles. Tubercle leading edges confine flow separation to the areas behind the troughs, which could minimize the chaotic turbulent wake that forms as a result of separated flow for a conventional hydrofoil. The tubercles also minimize spanwise flow. This is especially relevant to finite span foils such as rudders, as the tubercle leading edge could reduce the buildup of the trailing edge vortex sheet and the resulting distinctive tip vortices. Vortex interaction between the tubercle vortex pairs and the tip vortex might have further reducing effects on the tip vortex. Minimizing the turbulent wake is important, as its vortical structures cause drag, increase flow noise, and add to the non-acoustic signature that's detrimental to submarines, for example. I first had to select a reference rudder model, for which I chose one of the marine rudders that were analyzed by Folgowecker and Fellner in the David Taylor model basin. The reference rudder will be referred to as SLE for straight leading edge. It has a NACA 0015 section and a low aspect ratio of 1.5. It is also swept and tip tapered. Then I modeled two sinusoidal tubercle leading edge modifications with 4 and 7 tubercles, which will be referred to as TLE4 and TLE7 respectively. Both TLE rudders had a fixed tubercle amplitude of 5% nominal chord length. They were designed in a crest configuration, meaning that the last tubercle at the tip terminates on a crest. This way, the last tubercle vortex generated is of counter-rotating orientation to the tip vortex and may have potential cancellation effects. The 3 rudders were analyzed using detached eddy simulations in the computational fluid dynamics solver Star-CCM+. I chose the SSTK omega turbulence model, which performs better at predicting stall. I used a polyhedral cell mesh with low Y plus prism layers to resolve the rudder boundary layer. Initially, an 11 million cell mesh was used, which did not resolve separated flows accurately enough. Therefore, the mesh count was increased to 21 million, which improved these results. Simulations were run in the fully turbulent flow regime with a Reynolds number of 2.26 million. This was the highest flow velocity from the experimental reference study. You can see from the validation study here that there is good agreement between the experiments and my CFD. There are discrepancies for the maximum lift coefficient, but for the highest experimental angle of attack of 21.5 degrees when the rudder is stalled, the results were in good agreement, which gave me confidence in my model. Comparing the force coefficients of the 3 rudders, it can be seen how the tubercles produce more lift for every angle above 10 degrees. The improvements are most significant in the post-stall regime when the TLE produces 14 and 19% more lift for 25 degrees and 30 degrees angle of attack. At the same time, there was a large drag penalty from 20 degrees upwards, and the overall lift-to-drag ratio of the tubercle rudders could not be improved. The following slides show visualizations of streamwise vorticity scalars on spanwise cut planes. The very different flow profiles can be seen in this example case of SLE and TLE7 at angle of attack 15 degrees. For the SLE rudder, there is an onset of flow separation centralized on the trailing edge. The TLE rudder, in contrast, shows numerous small stall cells downstream from the troughs. it can be seen how the streamwise counter-rotating vorticity is initially generated at the leading edge and builds up over the surface. It significantly increases in strength around the stall cells. The tubercle vortex pairs have a compartmentalizing effect over the suction side surface, limiting spanwise flow. Still, the general spanwise flow component causes for the negative tubercle vortices to be annihilated. But the positive vortices persist within the downstream wake and break up the trailing edge vortex sheet and withdraw energy from the tip vortex. Co-rotating vortex interaction can also be seen between the tubercle vortices and the tip vortex, as the tubercle vortices are sucked into the tip vortex system and they merge. As the angle of attack is increased to 20 degrees, for the SLE, flow separation spreads out and becomes more severe. It spans across the entire trailing edge and begins extending forwards to the leading edge. TLE4 has confined separation between tubercle crest 2 and 4. Strong counter-rotating vortical elements form on either side of the stall cell, which are initiated by the tubercle vorticity. There is interaction between these vortical elements and the tip vortex, which causes first long-wave instabilities in the vortex path. The tip vortex also appears to be weakened in core strength, but has increase in circulation, which hints at possible diffusion. The impact on the tip vortex is much more significant for TLE7. Separation is confined to the tip area outwards from crest 4. This has a tip offloading effect, meaning it minimizes the lift generated in the tip area. The resulting pressure differences between rudder sides become smaller and a weaker vortex is generated. Secondly, large counter-rotating vortex structures again form on either side of the stall cell. These structures introduce further instabilities into the tip vortex. As a result, the tip vortex is heavily distorted in its trajectory and shows strong elliptical instabilities in its core. To further highlight this effect, I visualized the wake using Q-criterion visualizations. I displayed the turbulent kinetic energy on the isosurface to judge the strength of the wake. You can clearly see how the SLE tip vortex streams in a very coherent and straight-line path. The TLE7 tip vortex, however, shows long-wave instabilities and much lower turbulent kinetic energy levels. Its trajectory becomes distorted and interrupted, and it decays quickly. In the top view, it can be seen how the flow separation around the TLE7 rudder appears larger and more energetic. This strong near-field wake creates the drag penalties for the TLE rudders. However, it decays at an equal downstream distance compared to the SLE rudder. 3 chord lengths downstream from the trailing edge, only the tip vortex structures remain, which are much weaker and decay quicker for the TLE rudder. So for a naval submarine, for example, if a drag penalty and an increased near-field wake can be justified for accelerated wake decay a couple of chord lengths downstream, then the tubercle leading edge is an interesting modification. To finish off, the following conclusions can be drawn from this study. The tubercle effect, that is the formation of streamwise counter-rotating vortex pairs, resulting flow compartmentalization and increased lift, was successfully shown. The flow separation behavior was very different for the TLE rudders compared to the SLE rudder. As a result, the turbulent wake structure of the rudder was significantly altered by the TLE modifications in the following ways. The tubercle vortices broke up the trailing edge vortex sheet at low angles of attack. At higher angles of attack, streamwise counter-rotating vortex structures forming around the stall cells interacted with and destabilized the tip vortex. Most significantly, for TLE7, a tip offloading effect occurred that, together with vortex interaction, largely destabilized the tip vortex and accelerated its decay. These are the references that were used for this presentation. Thank you very much for listening, and please feel free to reach out to me if you have any questions.